G'day everybody. Today we're going to start talking about distributions and random samples. In this lesson we're going to cover how statistics behave when we take samples from a population, and we'll talk about how we can model the randomness of the proportions in these samples, and we'll look at two models in particular. So let's say we've got a population. I'm going to choose the example of people with blue eyes. So it could be the population of a country, and in this population there's a certain proportion that have blue eyes as opposed to other colours. We use the letter P to symbolise or to represent the population proportion. Now if we take a sample, it could be something like a survey from that population, that sample would have its own proportion of people that have blue eyes if it's come from the population. And to distinguish the proportion in the sample from the proportion in the population, we use P hat. So it's P with a little hat on top. When we use that, we are representing the proportion of people with blue eyes in the sample. And when we're using P without the hat, we're referring to the proportion in the population that have blue eyes. If we take different samples, we wouldn't necessarily expect each of those samples, even if they're the same size samples, we wouldn't necessarily expect that they're all going to have the same proportion of people with blue eyes. So while the population proportion, which we use P for, is considered constant, the sample proportion will vary somewhat from one sample to the next, and so the sample proportion may be considered a random variable. When we take that sample, we don't actually know what we're going to get, and it varies from one to the other. So this part of this topic on statistical inference is going to deal with the randomness of P hat. So I'm going to use the example of blue eyes. 32% of Australians have blue eyes, and so we've already referred to as P being 0.32. That's the proportion of the population that have blue eyes. If I take a sample of 20 people and count the people with blue eyes, I might have found that there are 6 people with blue eyes, and so we can now calculate the proportion P hat for that sample. So it's a very simple calculation. We're going to take the number of people with blue eyes divided by the size of the sample, which is 6 divided by 20, and we get 0.3. So P is equal to 0.32, and at the same time for this particular sample, P hat is 0.3. As we've already said, if I take another sample, I might find that 7 people have blue eyes, or 5 people have blue eyes. Maybe nobody has blue eyes. So it's a random variable. Because it's coming from the same population, we actually expect, and we actually refer to this as the expected value. The expected value of the sample proportion is the population proportion, which is another way of saying that on average, for all of the samples I take, I should get an average of 0.32. So let's have a look at what happens when we take lots of samples. What if we keep sampling 20 people at a time? So you might have seen this contraption before. We're going to drop a marble through the machine, and it hits the pegs and falls left or right. It's important to understand that each marble represents one sample of 20 people. And when that marble bounces to the right, there's a person with blue eyes in that sample. When it bounces to the left, there's a person without blue eyes in that sample. Because we know that the population proportion is 0.32, we expect that proportion to be 0.32. And so if we use that expected value and multiply it by the size of the proportion, we get 6.4, and that means that we expect the number of people in a sample of 20 that have blue eyes to be 6.4. So the average number of people would be 6.4. In reality, we get a lot of variation. So if I've dropped 30 marbles, in other words, if I've taken 30 samples, we can see we get quite a spread, quite a degree of variation. The most likely outcomes tend to be around 5, 6 and 7, or even 8. We get high proportions of samples that have those numbers of blue eyes. We get lower numbers of samples that have less or significantly more than 6.4. After 100 samples, you start to see the shape change a little bit. As we can see, we get in this particular case, we've suddenly got a high proportion of samples that have 8 people with blue eyes. At the same time, we've also struck a few samples that have way more than half of people with blue eyes, so up to 13 people in a sample of 20. If I leave this contraption running long enough, so after I look at 5,000 samples, we can start to see two things happen. First of all, the shape, which is something we've seen recently, and also even more variation. So here we've got evidence of samples having 15 people with blue eyes, and even samples of 20 people where not one of them has had blue eyes. So we can see that the process of sampling begins to look like a very familiar distribution, the normal distribution, in terms of the randomness of the sample proportion. There are two ways to approach this randomness with the sample proportion. We're going to look at one of each of those in turn. First of all, what we're talking about is really a binomial distribution in a lot of respects. So we could say that the sample proportion p hat is based upon a discrete variable x. We used x before to represent the number of people in the sample with blue eyes. So that's a discrete distribution. It's also, we could model it as a binomial distribution. And when we define a binomial variable, we need to define n and p. And so in our example, n is the number of elements in the sample, in this case the sample size. X, that variable there, is what we refer to as the number of successful elements, in this case the number of people with blue eyes. The expected probability, the probability that one person in that sample has blue eyes, is that expected value of p hat, the population proportion. Or more succinctly, in this example, if we want to represent the sample proportion p hat with a binomial distribution, we would use the discrete variable x, and x would be binomially distributed with n is equal to 20 and p is equal to 0.32. And so we could calculate probabilities associated with sample proportions using x. We have to keep in mind that we are using a discrete distribution now to represent something that's actually continuous. So let's look at a couple of examples, what I mean by this. So in our example where the sample size is 20 and p is equal to 0.32, we've defined x as being binomial. So if the question was what's the probability that a sample will have a proportion of exactly 0.3, we would need to express that in terms of the probability that x is actually equal to 6, because 6 over 20 is 0.3. Another example, a question might be what is the probability that the proportion will be greater than 2/3? 2/3 of 20 is 40 over 3. So we would convert that to the probability that x is greater than 40 over 3. However, x is a discrete number of people. So we would need to frame that in terms of the probability that x is going to be greater than or equal to 14. And we've seen in previous lessons how we calculate those probabilities with the binomial distribution. Let's look at another way to represent the same randomness, a different model. Because we saw after 5,000 samples our distribution starts to look like the normal distribution, we could use that distribution to approximate the distribution for the sample proportion. So we would say that the sample proportion itself is a continuous random variable, and we're going to call that random variable p hat. If we're going to define something as being normally distributed, it needs to have a mean and a standard deviation. The mean is our expected value of p hat, the population proportion, and we have a formula for the standard deviation. And in this topic, another word for that is the standard error. So the square root of p times 1 minus p, which is sort of what we mean by q, divided by n, which is the size of the sample. And so in this particular example, we would say that p hat could be normally distributed with a mean of 0.32 and a certain standard deviation. So let's look at how we calculate that standard deviation. Here's our formula. So I'm just going to input into that formula, substitute the value of p, which is 0.32, and the value of n, which is 20, and we get a certain standard deviation for this normal distribution. And so instead of a binomial distribution, we could represent the random variable p hat as being a normal distribution with a mean of 0.32, a standard deviation of 0.104. So just in summary, I've used this particular example of people with blue eyes. We've looked at a particular sample size of 20, and we've seen how we can use two different distributions to model the randomness of samples taken from this population. So first of all, we saw that we could use the binomial approximation, and that's to represent this approximation with a discrete variable x using the binomial distribution. The population proportion is what gives us p, and the sample size is what gives us the number of trials. It's important also to remember that a binomial distribution has its own standard deviation. We've calculated before as being the square root of n times p times q. At the same time, we could use a normal approximation to represent this distribution, or to model this distribution. So we could say that p hat is a normally distributed continuous random variable with a mean of 0.32, and we've calculated that standard deviation. That mean is the population proportion. 32% of Australians have blue eyes. That's our expected value or mean, and we've used this formula, which we'll see in the next lesson as well. We've used this formula to calculate a standard deviation. So in this lesson, we've seen how statistics behave when we take samples from a population. There's a lot of variation, but at the same time there's an expected value. With the variation or the randomness, we've used two distributions to model that randomness. Firstly, the binomial distribution, and we've also used a normal distribution. Please write down any questions that you have and complete the Google form to log your attendance, check your understanding. Thanks very much.